Okay, thank you very much, Ignazio, for your introduction. Actually, I think we met before the postdoc because you were in the jury of my PhD. So we but it's some time ago, and so thank you very much. Okay, so I will start this lecture about dense matter equatorial state, and I will mostly speak about the neutron star. So you will hear a lot about neutron star during this lecture. Okay, but before, so of course, I mean, this you can interrupt me whenever you want. And you can ask questions. You should stop me because we have a lot of time for the lecture. So do not let me rush on my slides. So do not hesitate to interrupt me. And just before I start, in order to show you that we could, I would like to make it interactive with you. So I received these questions that I think you have contributed to last week. These were the questions that you asked to Professor Meng. And among these questions, there is one question that I'm quite interested in, that I mark it in bold, which is question 9. Why are you interested in nuclear matter versus finite nuclei? So I don't know what are the answers, or what is the answer by Professor Meng, but my question is to you. So since you asked this question, so now, why do you think, I mean, it is interesting to develop or to study the link between nuclear matter and finite nuclei? So I just let you, this is a question for you. So what did you get from, I guess you had these questions, no? Last week. So you had answers on these questions, I guess. I don't really care about the answers of Professor Meng. I want to know what are your understanding of this question 9. So who wants to start? Yes. After you, so you asked the answer, you had an answer, but now you have your own thought. So what do you think about that, about this question that you answer, that you ask and for which you had answers?
From different methods like functional theory or initial calculations. Therefore, we can benchmark our calculations to improve our understanding of different interactions and also on many body problems. This is the one also for the method, which has an ideal system. The second answer for me is that method can be achieved in the core of the nuclear neutron stars, which is one of the frontiers in nuclear physics and astrophysics. Therefore, we can really get information from a real system, which is star, from the expanding of nuclear matter.
Okay, good. So you have two answers, and they are very good. So one answer is benchmark. So nuclear matter is nice because you can benchmark a lot of different nuclear physics models. And the second answer is because not only it's a benchmark, but it's also existing in nature. And these are neutron stars. Are there any other answer? I mean, so anyone else who would like to add something? Okay, so yeah, I think there are, I mean, these are the two main points and the two main answers to this question. Very good. Okay, so before I start, I would like to address, I mean, some of the questions that I will not give necessarily an answer, but which are connected to what we will discuss during this lecture. Okay, so the first one is, of course, related to the evolution of stars. Okay, so most probably you know that from the initial cloud made before, either directly from the Big Bang or before there are generation of stars which have contributed to enrich this interstellar medium into dust and different elements. You can have either small stars or massive stars, and I miss a little bit the pointer, but okay. So for here maybe I will use this pointer. Yeah. Well, okay. So either you have small stars, which create a red giant, then something that is called a planetary nebula, but it has nothing to do with a planet. It's just a name. And then it forms a white dwarf, or this cloud generates a massive star. And so this massive star creates a red supergiant, which explode as a core collapse supernova. And like, for instance, this is a Crab Nebula. And I also have a 3D version of the Crab Nebula. So you can also distribute it. And merci. Yes, OK, good. Ah oui, mais je suis là, c'est bon. Ouais. Okay, yeah, so this is the Crab Nebula. So you have a 3D version of it, which circulates. And so this Crab Nebula have been observed in 1054, so about 10 centuries ago, by Chinese astronomers, but also Japanese astronomers and Indian astronomers. And so it was a supernova, and now this is what we see from the rest, for the remnant of the supernova. And in the end of the 60s, a neutron star has been observed in the center of this nebula. And one of the interesting things is that it is one of the first pulsar which have ever been observed. Okay. Okay, the green. Okay, good, good. And the Crab Nebula is a very famous and well-known in the community, also because it radiates, it emits over from radio to gamma rays. So the aftermath of the supergiant star could be either a neutron star or a black hole. And one of the ways to characterize this aftermath is to evaluate the Schwarzschild radius. So this is the radius. If you have a star with this radius, then it means that nothing can escape from this system. Okay, so from general relativity, it is defined as being 2 times gravity constant times the mass of the star over c, the light speed to the square. Okay, and for a white dwarf, you see it's a very small number. And for a black hole, it is defined because you don't know really, you cannot define the radius of a black hole. So you impose it to be defined by the Schwarzschild radius. So this ratio is 1. And you see that neutron stars are not very far. So this ratio is about 0.2. So the Schwarzschild radius of one solar mass neutron star is about 3 kilometers. And the radius of a neutron star is about 12 kilometers. So you see that this ratio is not very far from one. Or at least it is comparable. Yes. Yes. Yeah. I guess I will give the slides. Yes. Okay. So this is one of the things that we'll discuss during the lecture. So the other one is about neutron stars, and they are appearing in various systems. So I just plot some of them. So you have pulsars, which emit pulse. You have binary neutron star systems, where you have two neutron stars circulating one around each other. You have X-ray binaries, so it's a neutron star which is absorbing a white dwarf or a main sequence star, okay, and is producing a accretion disk which is emitting in X-rays. Neutron stars could be extremely magnetic, and in this case they are called magnetars when the magnetic field is very large. And very recently, gravitational waves have been detected from the merger of two neutron stars. So they also emit gravitational waves. Okay, and that one of the questions which is extremely important. So this is not a very recent picture. You see, it is from 2001, and for a very long time, it remained like a good question, but no real way to give an answer. But now, with the advent of gravitational waves, for instance, one expects to be able to tackle this the question which is raised by this figure. And so what this figure represents are the different scenarios. So it's like a camembert. You can access through different rows here, which shows different scenario for the composition of a neutron star. So one possibility that a neutron star is not made of neutrons and protons, but it's just a quark star. And you have an expert here, Ignazio Bombacci is an expert of this very exotic system. So a neutron star would, in this case, a neutron star would be Hill name because it would be a quark star. Or you can have hybrid systems where you have, what you expect from a neutron star, but in the center you have new degrees of freedom, you have new particles, you have meson condensation, you have hyperons, or you could also have quarks, but only in the center. Okay, so the question that we try to answer based on signals and based on observations is to be able to decide, to trigger whether one or several of these possibilities of these scenarios are allowed for neutron stars. Okay, and the question is, so if for instance, you have something more than neutrons and protons in the center of a neutron star, it means that you have a phase transition, you have new degrees of freedom. And the question is, could we characterize these new degrees of freedom? Can we say something? And how? So how can we use the data, the existing data, or the future data, in order to go and to proceed on these questions? Okay. Of course, since we speak about dense matter, we also investigate the phase diagram of QCD matter that is represented here. So this is the axis with the temperature, with the density, and with the isospin asymmetry, Nn minus Np. And you know that not only neutron stars, but also nuclear physics experiments like heavy ion collisions, they also investigate this phase diagram. And what I would like to stress, so here you see, this is a picture, okay? So where you have nuclei at the bottom here, then you have hadrons, then you have this phase transition, and everywhere here you have this quark and gluon plasma. And what I would like to stress here or to emphasize here is a complementarity between what we can do on Earth in laboratories and what we can do, what we can learn from neutron stars. And one of the, and there are several differences, so we can understand this phase diagram, but there are also some differences. So the lab experiments, we have a very controlled energy deposition because this is a function of the energy of the colliding nuclei. The system is also similar in isospin asymmetry to the original systems. So if we collide nuclei which are close to n equals z, okay, even if last week certainly you have heard about exotic nuclei, but they are exotic but not as exotic as a neutron star. Okay, so the neutron star you have only at best 5% of protons. So this is totally out of reach with finite nuclei, where the asymmetry is not so large. Therefore, this phase diagram is explored close to isospin asymmetry. So it means close to n equals z. In neutron stars, in contrast, you have a lot of neutrons, or you have a system which is extremely asymmetric. So you have much more neutrons than protons. Okay, so you explore the neutron matter phase diagram almost. And you don't have a control of the energy deposition, because what you get as astrophysical observation is a global property. Okay? So for instance, it's a radius or it is a mass of this system. So which means that you don't probe a given density or a given energy, but you probe the things as a whole. And so what I would like to stress or to emphasize is that progress in this domain will certainly come from the combination of these two physics. So the laboratory experiment on one side and the neutron star astrophysical observation on the other side. Okay, another question that we will touch also is a question about the origin of the elements. So the elements that we find on Earth are not produced on Earth, as you know, they are produced in the cosmos, and they are produced in different environments. And this very nice Mendeleev chart provide a color of the elements depending on where they are formed. Okay, and you see, for instance, that hydrogen and helium, for instance, they are blue, and as you know, they are formed in the early universe during the Big Bang nuclei synthesis, BBN. And after you have different colors, but one interesting thing is that the two main colors are the magenta and the yellow. And if you look what it means, so the magenta is merging of neutron stars, and the yellow is exploding of massive stars. And all that are related to dense matter properties. Okay, so most of the elements that we find on Earth are produced in the cosmos, and in the and provided we understand what are the properties of dense matter, either in core collapse supernova or in neutron star merger. Okay, and the last point I would like to stress is about the link with cosmology. So I'm not an expert of cosmology. Certainly, you know much better than me about cosmology. So this is the picture which provides an explanation of where we are, and the early universe and the Big Bang is there. Okay, and we are somewhere here. Okay, so this axis is about the time which separates us from the Big Bang. So the idea is that when we look very far, we look in the universe as it was very early in the universe. Okay, so looking very far allows us to have access to how was the universe in its infancy. And you have here a picture which confront for the same view so it's a deep field, so it's it's a long time frame, long time exposure on a very small part of the sky in order to get the fainter system, the fainter galaxies. And here you see the same picture from Hubble and the new one from the James Webb Space Telescope. And you see that with the James Webb, you see much more. The first results that came out from James Webb is that there are too many galaxies in the, which do not seem comparable or compatible with the idea of the standard cosmology, and they are too big. And so no one really understands why. Okay, I don't understand why neither. However, if you look at the horizon of the future gravitational wave observatories, so you see here on this axis, you see the time from the Big Bang, and on this axis you see the redshift. Okay, so you can see, and this rows here shows how far we can go with the different gravitational wave interferometers. So the second generation, but also the one which is now under discussion, which is the third generation, the Einstein telescope or the cosmic explorer. And you see that it is able to go to very high redshift, so to the galaxy even before to the universe, excuse me, even before the galaxies are formed. So even before, let me show the next slide. So the next slide is the same ideas. You see the population of binary neutron stars here and the population of binary black hole here. And these circles are the horizon by different interferometers. So you have O3, which is there. You have Advanced Plus, which is improvement of LIGO. And then you have CE, which is Cosmic Explorer in red and in magenta. And in green, you have Einstein telescope. So you see, and here there is no population because there are no galaxies. And if you want to produce a black hole or neutron stars, according to the standard cosmology, you first need to have stars, and stars, they get born in galaxies. So you need galaxies. So if you don't have galaxies, you don't have stars, and you don't have compact stars, you don't have neutron stars, you don't have black holes. Okay, so there is a kind of cutoff. So if you go too far at too high redshift, you see too early in the universe, you expect not to observe any neutron stars or black hole gravitational waves. So this is what we expect, but this is a theoretical limit. And we already know from the James Webb that maybe the standard cosmology is not correct. So maybe this picture that I'm showing to you is not correct. So it is somehow related to the gravitational waves which are produced by black holes and neutron stars. Okay, good. Then my lecture, so I divided it in four chapters. So the first one will study together dense matter functional state, so the application to neutron stars. Then in the second one, we will understand the global properties of neutron star from general relativity, and they will and we'll have a hand-on session together on that. So I don't know if you have tried to compile the Python code that that have been distributed to you. So if yes, then it is good. If no, then we have until not tomorrow, but the day after tomorrow, either to do it, or if you have problems, just come to me, because I would like that we take this session to progress and to work on the code, and not to solve some technical issues. Okay, so if you have issues, so for those who haven't tried yet, so please try it before Wednesday afternoon. And if you have issues, just come to me and we'll try to solve it. Okay, so I expect, I hope that most of you will not have issues, but we never know. Then we'll address questions about crust properties of neutron stars. And finally, the last lecture will be related to astrophysical observations of neutron stars. And it was a suggestion that I can also dedicate some time to answer questions. So I think this is a very good idea that you had last week. And if there are questions during this lecture, and if I have not answered them, or if I have ill answered them, so please write it down, and we'll spend some time during the last lecture to answer these questions. And again, I have a question for you. So this picture shows, so I was coming by bus from France. In the Alps, there were a storm of a snowstorm. So you can see a lot of snow on the Italian side. On the French side, it was raining a lot, but it was colder on the Italian side. So you can see, so so there it was snowing, and these are some very little mountains. So my question to you, so are there mountains on neutron stars? And is it raining on neutron stars? Okay, so yes? There are no mountains? Okay, you have a few days to think about it. And the last lecture, maybe if I have time, I will try. I don't think there are any answer on that questions, but there are some maybe inputs, or maybe Ignacio, you will have also your answer. Yep. So yeah, so that's a question. So during the last lecture, I will ask again this question, and if you have any thought about it, I'm saying that there are no definite answer, because nobody have never been on top of a neutron star in order to measure if there are mountains, and nobody have never observed anything related to mountains. Yes. Is there any about the age of the mountains on a rocky planet? Is there any, so you can have a mountain which is as high as you want? Think about this. Yep. So I think it is related to this question. So somehow my question is not to say yes or no, but it is more to elaborate on if there are mountains. So imagine there are mountains. So what height it would have, and how you come. So the question is more how what is the logic or the demonstration that you are writing down in order to estimate, for instance, in case there are mountains, how high they would be on the surface of a neutron star. Okay. So let me go to the first lecture. Okay. No question about this introduction? So, so the first lecture is about dense matter equatorial state. Oh, what is that? Just one moment. So I already had this problem before, but it got solved. Yeah, it seems okay. Good. So it's just it gets solved by itself. Okay, so yeah, I would like to say a few words about the Landau theory of Fermi liquids. And it is not only because we are on the Fermi street. I mean, this is really how it is called. So let me just remind you, in particle physics, when we speak about particles and antiparticles and the creation threshold and so on and so forth, what we have in mind. So what picture we have in mind. So this is the energy axe, and you can see the zero, and you know that there is a gap, which is given by the mass of the particles. Okay, so you have plus mc square, whatever is a particle. Imagine if you want, if you need an example that they are electrons, but they can be anything. And you have minus mc square, you have this gap. Okay, and below there, all states are occupied, and this is called the Dirac sea. Okay, you have, for instance, all these states which are occupied, and their dispersion relation is given by this relation. And what you call particles, so for instance, electrons, are there, okay, and they are following this dispersion relation from special relativity. Okay, so this is nothing else than what you have learned in particle physics. And when you bring some energy in the form of a photon, for instance, so this is my gamma ray here. So what he does, it creates a hole, okay, and it brings, and if the energy is larger than 2 times the mass, so this energy gap, then the hole, this state, is promoted and becomes thicker. Okay, so you have an energy, so you should provide an energy which is twice the mass in order to have an electron and a positron together. Okay, so this is when you create them, and when they annihilate, they produce some energy in terms of a gamma, and the energy is about twice the mass of the electrons. Okay, so this is the usual picture from particle physics. So again, so what is a picture from nuclear physics and how it goes? Okay. So what is the different? What are the differences? So most of the things are the same, okay, because this is physics. So physics is unique. But what you have on top of this picture in nuclear physics is that you have what is called the Fermi sea. Okay, so the particles here are not in the vacuum, they are in particle physics. They are in medium. And the medium is represented by this Fermi C, okay, which is a continuous, not for necessarily continuous, excuse me, but it is a set of states which are occupied up to a given energy, okay, that is called the Fermi energy or the Fermi momentum, so EF or PF. Okay, and so this is the ground state. Okay, so this is a representation of what we call ground state for the Landau theory of Fermi liquids. And what is an excited state? So an excited state is very similar to what you have here. So you take a you take a state here. So you create a hole. So this is my little circle, and you promote this hole to this particle state, which is my cross. Okay, and it costs you this small energy difference. And if you do that close to the Fermi level, it costs you almost no energy. Okay, so if you have a state just below the Fermi level and you can promote it to a state just above, it is almost of no energy. So if you are in a finite system, you know that you don't have a continuous state, you have discontinuous states, okay? So it costs you the shell gap that exists between the last occupied state and the next one. But if you are in uniform matter, you may have excited states that start right after the ground state and cost you almost zero energy, okay? Or a little amount of energy. Okay, and just to make a link with particle physics, you can also create a hole in the anti-particle state and promote it there, okay? Not here because all the states are Pauli blocked, okay? We speak about, so it means that you have the Pauli principle to respect, and you can promote a state which is there into these empty states which are sitting above the Fermi C. Okay, so no problem with this picture. So you see, I represented the Fermi C vertically like that with a momentum, and then I just turn it on this side, and I add on this axis the occupation number. So as I said before, since we are dealing with fermions, the occupation number is 0 or 1. Yes? Why the Dirac? Well, this is the interpretation by Dirac that you have, a state of a state. You have a set of states which are occupied, and the creation of an anti-particle is a hole in this Dirac sea. Okay, this is the. Excuse me. Yes, exactly. Yes. So we are speaking about fluctuations in the vacuum. Okay, you bring an energy and you can create a pair of particle and antiparticles. But what I wanted to stress, okay, is that this classical picture that you have learned at school in nuclear physics is very similar. It's not much different. The only difference is that instead of having the vacuum here, you have a set of fill states there. Okay, so that's the main difference. But apart from that, we are speaking, this is the same physics. Okay, and and we can speak about ground state and excited states, and the ground state is represented by this Heaviside function. Okay, so it means that in the classical Fermi system, you have all states. If it is uniform matter, And if it is finite nuclei, okay, it don't have a continuous state, you have some discontinuities, but the idea is the same. All the states below the Fermi surface are fully occupied with occupation number 1, and all the states above the Fermi surface are not occupied with the Fermi occupation equal 0. Okay, so this is the Fermi liquids. And you can represent this distribution of particles in terms of the Heaviside function. Okay, so now exactly like in particle physics, we can do some second quantification formalism. So let me call, so my state, which I picturize here, I give it a name, so it is GS, ground state. Okay, and how do I create a particular hole in this, on top of this system? And so it is exactly like in particle physics. So if I want to create a hole, I have to annihilate a state in my ground state. And if I want to create a particle here, I have to create on top of the ground state a particle. So a hole is the creation operator, call it as you want. I call it A with quantum numbers. In this case, for uniform matter, it is P. But if you do finite nuclei, for instance, it is a set of N, L, J, or whatever quantum numbers associated to your system. And if it is a particle, then you have to create it. So it is a dagger on top of the ground state. And now I can also define a density operator. Okay, so what I have to do is I have to make a summation over all the occupied states. And so I have to read it from the right to the left. So what I do is that I destroy a state and then I recreate the state. Okay, so it's like an identity operator. First I destroy because it is occupied. And then after I restore it, at the end, the system is as it was before. But the result is that I'm counting the number of particles. Okay, so okay, so suppose now that I want to write the wave function in coordinate space. So my quantum numbers here for uniform matter is represented by P. Okay, and I project it in coordinate space R. And this is my wave function that I think you are used to. So phi P of R is just this bracket, the Dirac, yes? Yeah, right. Yes, the summation, yes, here. Well, it can be larger, that's correct. So I can also sum over all P's, but every P above PF will give 0. Okay, so it is only if P is less than PF, then I will have 1. Okay, but in principle, you are right. I can sum over all P because I know that if P is larger than PF, I will have 0. Okay? Yes. Okay. So, excuse me. Okay, so let me try to see if it works correct. Okay, so the wave function in coordinate space, you can do the exercise with me. So what it is, so imagine that you are wondering about the wave function of a whole space, a whole space state, excuse me. Okay, so it is, you take you take the whole definition. Okay, so this is AP on the ground state, if it is a whole. And if it is, and if you want to have the wave function of a particle, Okay. So this is what you should do if you want to have the wave function of a whole or of a particle in second quantification. Is it? So in principle, it's just to warm up, so to remind things that are familiar to you. Someone asked me if the slides will be given, and I will give the slides with I mean the corrections or with what I have added. Okay, let's continue. So we continue to deal with Fermi liquids, and we have to, as you know, it's a quantum system. Otherwise, I would have spoken about Boltzmann gas. Okay, Boltzmann is classical, but fermions or bosons, they obey to quantum mechanics. So in order to get the wave function, I have to solve the Hamiltonian. And let's take a non-relativistic Hamiltonian. So I have so I can create the Hamiltonian as a summation of kinetic energy and potential energy. Okay, and the kinetic energy, non-relativistic, is the one that you are familiar with. So it is h bar square, p square over twice the mass. And you have also the potential energy. And the potential energy, if you are in uniform system, okay, it cannot depend on the coordinate. Okay, so it's a quantity which is constant in space. And so if in uniform matter you want to solve your Hamiltonian, you obtain from it the single particle energy, what I call EP. Okay, and the single particle energy is also a contribution from kinetic energy, h bar square p square over 2m. Okay, so now it's a vector p. It's not anymore an operator like here. And you have the mean field that I called sigma 0. For the moment, I will not care too much about the interaction. Okay, so I don't elaborate too much about the mean field. But it is a constant contribution. And my wave function is a wave function of plane waves that I can write. So I have to identify a volume in which I will normalize my wave functions. Okay, so this is the reason why I have the volume. And you see, so this is a propagation of a plane wave. Just, I mean, because I get confused sometimes with P and K. So I try to, at least in this slide, to write it correctly. So P is defined as h bar K. Okay. And then I just ask you to write the energy density. Okay, so the number of particles per unit volume, which is an observable obtained from the quenching of the ground state. Okay, so it is the energy density in the ground state of a Fermi system. And I ask you now to use this definition of the number density quench on the ground state in order to determine what is the energy density of a Fermi system in the ground state. Okay, so we can do that together. So it is my ground state. Then I have to replace my density operator by what I have written before. Okay. So now I put the summation out. So I will make the summation okay. And now I think you know that if I take that, I got identity that I inject right in the middle, and therefore I obtain okay. Is it so? All these steps are very simple steps. No question up to now. Uh, so this is my wave function. Okay, so I have now to integrate over D3R. And because my wave functions are normalized, this gives me 1. And therefore, okay, so I have to sum just 1. And of course, let me change my color just to maybe blue. Between this step and this step, I have to sum over k less than kf, okay, because otherwise my operation, my creation or destruction operators will give me just 0. Okay, so what does my yes, excuse me, I will put another color. Here, okay. Where should I put it? Yes, it should be here. I have to put this normalization, which are there, of the wave functions. Okay, so what does it say at the end? It says that my density, it is 1 over the volume in which my mesoscopic volume where I work, and I have to make a summation over all the states, the whole states which exist up to the Fermi momentum. Okay, so this is really the picture of the density, because this is the number of particles. It counts the number of particles, and if I divide by a volume, so it gives me a density. Okay, is it clear to everybody? Yes, no? Okay, so let me continue there. So I assume that this expression is correct. So I have 1 over the volume. And then I am in infinite matter. And I have to sum over all the momenta. So it is not very consistent because my distribution of momenta is continuous. Then I have to change my summation into an integral. Okay, and I will give you the rule that I will demonstrate in the next slide. Okay, so the summation over k is the same as taking the volume over 2 pi to the 3, the integration over d3k. Okay, so this is the same as writing the summation over k. And of course, k going from 0 to kf of 1. Okay. And so d3k, it is, so there you see there is no angular dependence. So it is 4 pi k squared dk. So I have the volume here, which cancels out. So I have 4 pi divided by 8 pi to the 3. And I have to integrate dk k squared from 0 to kf. Okay, so that gives me kf to the power 3, okay, divided by 6 pi squared. So at the end of the day, I have demonstrated that my number density okay, so the density of particles in the ground state of Fermi liquids is simply kf to the power 3 divided by 6 pi squared. So it's very simple, and this is the result of the way we define the occupation number. Any question? Sounds clear, or it is not clear at all? I hope it is clear. Yes? Okay, good. Okay, so let's continue. Yes, so I said that I would like to demonstrate this, this rule of going from discrete summation to an integral. Okay, so just to make it simple, let's suppose that I am in a one-dimensional case. Okay, so this is given by x, which is there. Okay, and so I have my unit length where I normalize my wave functions, and I define some boundary conditions. So all my states after xi and after xi plus L are continuously connected. Okay, so it means that my wave function in xi plus L is equal to my wave function in xi. Okay, and if the wave function are given by plane waves, so that means simply that my exponential minus ik xi plus L should be equal to my exponential minus ik, excuse me, xi. Okay, so which implies, if I want to make this connection, that k times L is equal to a given units that I call n times 2 pi. Okay, so it means that my momenta are n times 2 pi over L. Therefore, when I write my discrete summation over k ki, okay, I can say that okay, it is integration over dk, but I have to divide by my unit in k. And how do I define my unit in k? I can define it from there. Okay, so k is n times 2 pi over L. So my unit step in k is 2 pi over L. Okay, so if I was working in a one-dimensional system, I would have to divide by my unit, so L over 2 pi, the integration in 1D of k. Okay, and now in the 3D case, so let's say that I have a delta k vector. So instead of having only 1D, I have 3Ds. Okay, so my unit in D3k is 2 pi to the 3 times L to the 3, and L to the 3 is the volume. Okay, so my summation over k in 3D now is equal to the volume over 2 pi to the 3 D3k. Okay, so this is what I have used in the previous slide in order to change my summation over the momenta into integral over a continuous variable, which is k. No question up to now? I guess everything is clear. Okay, so let's continue. Now, up to now, I have spoken about a system like an electron system, but I didn't spoke about the spin of the electron. Okay, and you may consider that your system is in a spin, in what we call the spin saturated system, which means that there are equal number of spin up and spin down. So you can treat spin up and spin down equally. Okay, they are in the equal number. Okay, so the wave function. So if they are equal spin up and spin down, so the expression before, so the summation over the momenta, can be done for spin up, and you multiply by 2 in order to treat spin down at the same time. Okay, so you can introduce a degeneracy coefficient that is called usually J. Okay, and for instance, spin saturated system, you will count the system for one spin and you will multiply by 2 and it will work for the 2 spins. Okay, so J equal 2. So the density is not anymore the summation of 1, but it is the summation of 1 times the degeneracy in spin, if you have equal number of spin up and spin down. And if you don't have equal number, then you count the number of spin down, the number of spin up, okay? And you will have 2 distributions associated to the 2 kind of spin. Okay, so now just a question. Suppose that instead of electrons, you treat nucleons. Okay, and that nucleons, so first you suppose that you have equal number of spin up and spin down. And second, you suppose that you are in symmetric matter. So it means that you have an equal number of neutrons and protons. Okay, so what would be the degeneracy associated to this system? Uh, there, here. I'm not sure. I'm not sure, but I mean, because is yeah. Ah, yes, yes, you're right. Yes, you're right. Um, it will not have an impact in the rest of the lecture. But that's correct, yes, because of the Pauli matrices. Okay, so what would be the value J for symmetric nuclear matter? Okay, so you have, yes, 4. So this is 2 for the spin times 2 because we are in symmetric matter. And therefore, you have equal number of neutrons and protons. Okay, so this is the isospin. Okay, and you can play also the same game in case of quark matter. Okay, so suppose that you have degenerate UDS matter, so you have equal amount of U, D, and S quarks. Yes, because you have massless quarks. Correct, correct. Yes. So I suppose that they are degenerate. They are the same number of up, down, and strange quarks. Okay, so what would be the degeneracy that I should consider in this case? Okay, so of course, I have 2 for the spins. Okay, so the flavor, I said UDFs are degenerate, so I have 3. Is that all? Yes, it's finished. So it is 6. And colors. Okay. And how many colors? 3. Okay. Okay. So in this case, if I treat this quark system of UDS degenerate, I have to consider that the degeneracy of 18. Okay, no question? Okay, so let's continue on the Fermi gas and treat explicitly the free case, so without interaction. So how would I compute the energy? Okay, so I give an expression here. So my total energy, so I like to work in terms of energy density, okay, because I divide by the volume. But the numerator is just the energy. So this is my degeneracy times. So this is my single particle energy, the one I presented, introduced before, EP. Okay, and then if I want to have, it is the same as with the number of particles. If I want to have the total number of particles, I have to count and add all particles. Now, if I want to have the total energy, I have to add all the single particle energies. Okay, so I make a summation over the momentum of my single particle energies. And then I do the transformation of discrete sum into a continuous integral. And then I integrate over the momentum my single particle energy. And then I can have two cases. So either the non-relativistic case or the relativistic case out of which I will extract the ultra-relativistic case, so the case where the momentum is way larger than the mass. So I can neglect the mass and my single particle energy is just the momentum. In the non-relativistic system, okay, you see there are two terms. So the one you are used to, and of course the rest mass energy. You know that in the non-relativistic system, the energy is known up to a given constant. So in principle, you can decide whatever constant you wish to put. But if you want to make a good connection with a relativistic system, so the constant is not free and it is given by the mass. Yes. Yes. Yes.
And this is a consequence of special relativity.
Yep.
You do not have the contribution of
MC square. Yeah.
Just the mass.
Yeah. In fact, in another, yes. And the constant, because you can, yeah. Well, I have an effect of special relativity. So in non-relativistic approach, I don't know how to scale the energy. So I know the energy, but it is given at a given constant. And my constant, I can take it to 0 if I wish, but I can take any number. But it can be 0. But if I want to make to have a connection with relativity, my constant is not free. It is the mass, the rest mass. But of course, if you don't make the connection with relativity, you can remove this constant, okay, and take it to be 0 or any number. Okay, but yeah, I think yeah, I think that in our case, since for neutron stars, you increase the density and you reach the relativistic limit, you have to make such that your non-relativistic description matches correctly with the relativistic. Okay. Okay, so if I play this game and I replace my single particle energy with either the non-relativistic expression given here or the ultra-relativistic expression given here, then I have these two expressions. Okay, so the mass term mc square is just a constant, so I have to integrate over d3k, and you 2 slides before we have seen that the integration over d3k gives you the density. Okay, so this is the density times mc square. This is the energy density. And you have to integrate p square over d3k, and then it gives you p to the 5th divided by 5. Okay, so this is the origin of this 5. And in the p to the 5th, you have p to the 3, which defines you the density, and then you are at the end you have only the p square. Okay, and this is the energy density, and what I use as a capital as a small e the Roman E is my energy per particle. Okay, so in the rest of the lecture, when I use Latin, Greek letters, it means a density. And when I use Latin letters, it means per particle. Okay, so it can be an energy density or an energy per particle, but it can be also an enthalpy, an entropy, whatever. Okay, and so this is my expression for the non-relativistic energy, density or per particle. And for the ultra-relativistic energy density, I have to integrate over d3k times k, so it is k to the 4, which explains why I have k to the 4, so it's k to the 3 that defines my density, which is there. 1/4 is because of this k to the 4, and then I kf to the, and then I have only a linear function of pf. Okay, so so now the exercise is very simple, because what I ask you to determine, to extract from this expression is, suppose you have an energy density given by this expression. So can you write down the energy per particle, which is given by this Latin number, Latin letter? Okay, and it's very simple, okay, because the energy per particle, so maybe I can write it here. So E with Latin number is energy per particle, okay, and I can say that it is an energy per unit volume times volume divided by particle, okay, and by density, what it is my number of particles divided by the volume. Okay, so the total energy divided by the volume is my energy density. So I use Greek letter epsilon, okay, divided by n. Okay, so that's very simple, and using this relation, you can determine, or this relation, you can determine what is the energy per particle of a non-relativistic system. Here. Yes. Energy, yes. Yes. In the ultra-relativistic. Yep, exactly. And because the density have kf to the 3. Yes, correct. Okay, so my energy per particle. Okay, so I take my energy density and I divide it by the density. Okay, so this is mc square. Okay, plus 3/5 of pf square over 2 times the mass. Okay, and I can also write it like mc square. And the Fermi energy is the energy of the last occupied state, which momentum is pf. So the Fermi energy is pf square over 2m. So plus 3/5 times the Fermi energy. Okay, with the Fermi energy equal pf square over 2m. Okay, and the energy per particle in the ultra-relativistic limit is 3/4 times pf. C. Okay, so this is 3/4 times EF. Okay, so let me write it non-relativistic and ultra-relativistic. So in the ultra-relativistic limit, the Fermi energy is just PFC. Okay. Okay, so let's continue. No question up to now? Okay. So, yes, so this is what we obtain at the end. So the energy per particle is just defined as mc squared plus 2/5 times Fermi energy in the non-relativistic limit. And that I have given in the previous slide. Okay, so this is just pf squared over 2m. And I have the same expression for the Fermi energy in the ultra-relativistic limit. So this is pfc. Okay, so now for the rest, I prefer to express it in terms of the density and not on as a function of pf. So the next step is just to transform all the PF, so to use this relation for the density, and to every time you have a PF or a KF, it is a power 1/3 of the density. Okay, so you can write now the energy density as mc squared okay. So I have h bar square over 2m, and I have 6 pi square over j, so to the power 2/3 times the density to the power 2/3. Okay, and in the ultra-relativistic case, I have 3/4, and the density gives 6 pi square over j to the power 1/3 times the density to the power 1/3. Okay, so now you know how the energy per particle scales with the density in the non-relativistic limit. So it is n to the power 2/3, and in the ultra-relativistic limit, it is n to the power 1/3. Okay, so these are quite simple algebra, and we will come to the calculation of the pressure. So does anyone remember the thermodynamical definition of the pressure? So suppose you have a piston with an action given by a force F. So S is a surface. So do you remember the relation between the pressure, the force, and the surface? Yes, okay. So F, so let me write it like that. Okay, F equal P times S. Not writing very well. okay? And the force is a gradient of an energy, okay? So it is minus a gradient, so it is d over dr of an energy. Okay, so by comparing these two, I can extract that the pressure is something like dE over S dr, which gives me a dV. So it is a dE over dV. And of course, in my piston, I conserve the number of particles. Okay, so it is so this is how I define the pressure. So what is the pressure? So the pressure is the energy, it's minus, so there is a minus sign, but this is the variation of energy due to the compression, to the variation of a volume at conserved number of particles. Okay? So, yes? Yes. But in fact, at the end, because the other term is a constant, you can include it in the definition. Yes, yes. For the moment, it is 0 temperature. Yeah. Yes. Yes, but it is a constant. So if I differentiate a constant, I don't care. It's 0. Okay? Okay, so this is my definition of the pressure. So it's a variation of energy. And before, at a constant number of particles, and before I was calculating the energy per particle. Okay? So my pressure is dE over N divided by V over N, okay, at N and constant entropy. Okay, and remember that my energy per particle, I use Latin letters. Okay, so E, so my Latin E is an energy per particle. It's capital E, total energy per particle, divided by N. Okay, and V over N is 1 over the density. Okay, so when I divide by 1, when I derivate with respect to 1 over the density, it is dN over N squared. So at the end, I have N squared dE over dN, okay, at constant entropy. Okay, so if I want to obtain a pressure out of my energy per particle, I have to derivate with respect to the density. I work at 0 temperature, so I don't care, and times N squared. So I just remind you what we have obtained before. So the energy per particle, I don't know why it is shifted left. So here it's better. So this is my energy per particle in the non-relativistic limit and in the ultra-relativistic limit. So this is what we obtain, okay? N to the power 2/3 and N to the power 1/3. And therefore, by applying this simple expression, you can compute the pressure in a non-relativistic case and in the ultra-relativistic case. Okay, so the pressure is N squared. So I divide E by N which is power 2/3. So I have a 2/3. E non-relativistic, okay, and internal divided by n. Okay, so here what I wrote is that this piece is my internal energy. Okay, so it gives me 2/3 of n non-relativistic internal energy. Okay, so the internal energy scales like n to the power 2/3 times n, it is 5/3. Okay, so I can say that it is just a constant that I call k times n to the power 5/3. And if I compute k for for electrons, excuse me. Okay, I obtain something like 4 times 10 to the power 4 MeV Fermi square. And I can do the same for the ultra-relativistic expression. So it is n squared, 1/3 of the ultra-relativistic energy divided by the density. This is a result of my derivative. So this is 1/3 of n ultra-relativistic. So this is a coefficient. So times n to the power 4/3. And this coefficient is 120 MeV Fermi. Okay, so now what you have, so this is very important for the rest of the lecture. So you know that the pressure in the non-relativistic limit scales with the density to the power 5/3. In the ultra-relativistic limit, you know that the density scales with the density to the power 4/3. And I just remind you that in the classical limit, so when you have for a Boltzmann system, the pressure goes like N R and T the temperature. And this is the same whether you are in a relativistic or non-relativistic limit. So I think I still have some time, no? Yeah? Of course, I mean, yeah. So I just ask you how much time I have. Okay, so 7. Okay, so I will finish with this density temperature phase diagram. So there, I just write again the expression we obtain for the pressure in the different limits. Okay, and here a diagram with temperature versus density. Do not look at the numbers for the moment. And now let's just identify in this phase diagram where are the classical and the Fermi limits. Okay, so it is written there. So if you go at high temperature and you are low in density, okay, you will, so this is our normal world, for instance, we are at high temperature, low density, and this is a classical limit. However, if you decrease the temperature, and at the same time you increase the density, then we enter into the degenerate or quantum system. And since we deal with fermions, this is what I call here the Fermi limit. Okay, so in this diagram, you can already identify two regions. Now, if I am at low temperature, okay, so my velocity is low or low density, then I am in the non-relativistic limit. And if I am at high temperature, so my velocity is large, or at high density, then I am in the ultra-relativistic limit. So in this case, so here it is high temperature or high density, it is the ultra-relativistic limit. And low temperature or low density, it is non-relativistic limit. So now I have 4 domains here, which defines the difference, I mean, between ultra-relativistic and non-relativistic, and between quantum and classical limit. So now I try to be more quantitative. I would like, so for instance, imagine that I am here and I increase the density from low temperature. So I go from the classical non-relativistic limit to the Fermi non-relativistic limit. And I want to know when is my intersection. So when I change my description. Okay. So in the classical non-relativistic limit, the pressure is NT. So I just look at where my classical pressure, NT, is equal to my Fermi non-relativistic pressure, which is K times n to the power 5/3. Okay, so I have to look at the intersection between these two curves. So since I prefer to work in log scale, because you see that we are going through a large number of densities and temperature. So what it means is that my log n is going like, my log t is going like my log n to the power 2/3. So I just draw a line, and the slope that is here is 2/3. Okay, so this is my first equation. So now I continue to increase, and I want to know when I go from the non-relativistic degenerate limit to the ultra-relativistic degenerate limit. And therefore, I do the same. So I look at the intersection between the two pressure. And what I obtain here is that it is just a straight vertical line. So it defines, so my transition occurs whatever is the temperature, always at the same density, which is the ratio of these numbers. So this is the reason why I gave their value before. Okay, and I obtain this number that I report here. Okay, so here, this is a transition between non-relativistic and ultra-relativistic limit. So I just remind 1 and 2, okay, what it means in this construction. So now I want to know, so I do the same thing, but between the classical and Fermi pressure in the ultra-relativistic limit. Okay, so I have to equal this guy with this guy. And when you do this work, so you realize that you have also a straight line, log t versus log n, but instead of having a slope of 2/3, you have a slope of 1/3. Okay, so I put a lower slope here. And this is my equation which defines the limits between the two. So now I want to know when equation 1 intersects equation 3. Okay, so you take equation 1, equation 3, and you look at the intersection, and you see that the intersection is given by the ratio of these constants, which is the same as definition of there. So here you have a points. So you go from this regime to this regime at the same point here than the transition between the non-relativistic and the ultra-relativistic limit as a Fermi limit. I'm almost done. So now I'm looking at this intersection, and I want to know what is the temperature. Okay, so I take this, for instance, I replace n by this density here, and I obtain a temperature which is about which is compatible. I mean, a fraction of 10 to 10 Kelvin. Okay, so you see with yeah. So yeah, you are right. I am in a regime where for the quantum system, the temperature that we consider here remains small. And therefore, I use temperature independent relations. However, in the classical limit, this is not a small temperature. And why? Yes. And why? Exactly. That's a typical Fermi. Why I say it is small or it is large? It is because I compare this number with a typical Fermi energy, and the typical Fermi energy is MeV, and this is smaller than MeV. Okay, so it means that I am for the degenerate system. I can approximatively say that that the temperature is zero, but of course for the classical system it is not zero because the pressure is a function of the temperature, and there is no Fermi energy for a classical system. Okay, I think I will stop here. Okay, thank you, and we can have questions if or.
The next lecture you will discuss the equation of state and this region number 2.
No, I will. Just one thing I forgot, that there is one additional information I wanted. So now, if I take my phase diagram and I put the system that you know, like for instance normal metals, or the sun, or white dwarf, or neutron stars. So they are lying here. Okay, so neutron stars are, so I put it in the ultra-relativistic limit because I had in mind the density in the core of neutron stars. The white dwarf, they are not very dense. So therefore, there are the transition between the non-relativistic limit and the ultra-relativistic limit. The sun is not a degenerate system. It is a classical system. Okay, so the statistics that describe the sun is a Boltzmann statistic. And normal metals, I would put it at low temperature and low density, but in the Fermi regime. Yep.
You have the integral spatial of energy density using the relativistic energy for a
Yep. Yes, and it's not simple. Exactly. Yes. Yeah. Yeah. Yes. For nucleons, yeah. Yep.
Because the density is not the same. Number density is not the same if I consider electrons and if I consider particles. Okay.
Yeah, because you have a factor 2000 in the mass. So that's mainly the mass which scales it. Yep. Okay, so so the classical limit is a limit of a Boltzmann gas, which means that you don't invoke at all quantum mechanics. It is, for instance, the atmosphere in this class is described by the Boltzmann distribution. Okay, it's not a quantum system. But as soon as you look at the distribution or a statistical distribution in, if you are doing statistical quantum mechanics, then you realize that you have two kinds of distributions, which are the fermionic distribution and the Bose-Einstein distribution. That depends on the spin and what the system that we describe, electrons or nucleons, are spin half, one half, so they are fermions. And their distribution is then therefore governed by the Fermi distribution.
Which is Boltzmann distribution and also the Fermi distribution, and the third one is Bose-Einstein.
Yep. Okay, and then you have the Pauli distribution or the Pauli blocking, which impose that you could overlap only systems with different quantum numbers, but if they have the same quantum numbers, they cannot overlap.